Okay. So, after second iteration we have just seen that voltage V2 is 0.98578, angle is of course in distribution system very small. So, 0.085 degree, V3 is equal to 0.96590, angle 0.36 degree, and V4 is equal to 0.95137, angle 0.5. These are all in per unit, right. All calculations are in per unit, right. Everywhere I have not written per unit. So, here again you can see that all the angles are leading angle, and I ask you also that why instead of negative, why this positive angle is coming. Answer is very simple, but you please find out what is I mean why it is coming leading angle for this example, right. Next is that power loss calculation, right. What will be the power loss? There are your 2-3 ways of computing power losses, right. One is that suppose you have a distribution network. I will show you the two different ways, right. At least 2-3 ways. This suppose you have a power network, distribution network like this. This is your substation, this node is 1, suppose this is 2, 3, 4, 5 and 6, this is the distribution network, right. And current flowing through this first branch, very first branch, this is your say I1. Everywhere load is there, I mean everywhere. For example, here it is PL2 plus JQL2, say similarly here PL3 plus JQL3 and so on. Everywhere loads are there. I am not showing here, but everywhere loads are there. Suppose net injected power is power coming to the substation. This is substation actually, power coming from the grid to the substation. Suppose it is PS plus JQS, right, and it's your impedance of this branch, very first branch, say it is Z1. So, whatever, but from the load flow studies, you know this your what you call that branch current I1, and this voltage, substation voltage is known to you. This voltage is V1 is equal to, in this case 1 angle 0 we have taken. So, then this current is also known from the load flow studies. Then what you can do is you can write this equation PS minus JQS is equal to V1 conjugate I1. This is the power coming from the grid to the substation. So, you can write the way you have studied in the load flow studies, PL minus JQL is equal to V conjugate I. So, PS minus JQS is equal to V1 conjugate your I1, this is the current, this I1, right, and I1 current is known to you, and V1 is equal to 1 angle 0 degree, therefore, V1 conjugate is also 1 angle 0 degree. That means, my PS minus JQS is equal to your 1 angle 0 degree into I1 is equal to I1, everything is in per unit. Therefore, PS is equal to real part of I1, right, and QS is equal to minus imaginary part of I1, because it is P minus JQ. So, PS minus JQS, it is minus imaginary of I1. That means, this PS and QS coming from the grid are entering into this your what you call substation, and that means this power is equal to whatever loads are there, whatever, suppose you have NB number of nodes, suppose you have NB number of nodes, and you have all the PL QL is known. So, what will be the then total load? Say total load will be TPL will be your sigma I is equal to 2 to NB, and this is PLI, this is the total load, and total reactive load, this is real power load, it is QLI I equal to 2 to NB, right. That means, this is the injected power, and injected power PS actually is equal to total power TPL plus total power loss, right. That means, P loss is equal to PS minus total real power load. Similarly, your Q loss is equal to QS minus total reactive power load. That means your P loss is equal to the power injected at the substation, that is PS minus the total TPL, right, that is total real power load. This is the P loss, and Q loss is equal to QS minus I is equal to 2 to NB QLI. This is the power loss, right. So, this is in per unit, this is in per unit. whatever you will get PS or loss, everything is in per unit. So, you have chosen 100 MVA base. Therefore, this quantity, as soon as you this quantity you multiply, for example, PS as soon as you multiply PS is equal to real part of I1, this is your PS. If you multiply it by MVA base, then it will be megawatt. Then this quantity if you multiply by 1000, it will be kilowatt, right. Therefore, real of I1 into MVA base into your 1000, that is kilowatt, and MVA base is 100. That means, this quantity, this whole quantity, hold on, I am writing here, this whole quantity PS, right, is equal to real of I1 then into 100 MVA base into 1000, this is kilowatt. That means, PS is equal to real of I1 into 10 to the power 5 kilowatt. Similarly, QS also will be minus imaginary of I1, right, into 10 to the power 5 kilohertz, right. So, this way, this is one way, another way is I square R loss you can compute. So, this way you can compute, that means your power loss, that real power loss P loss is equal to if you put like this, that is your PS. Suppose if it is in kilowatt minus total load TPL, that is also in kilowatt, that will be PS loss, right. That means, TPL is sum of all the your real power load. Similarly, Q loss also it is QS if it is in kilovar minus TQL, then your kilovar. So, this is P loss and this is Q loss, right. So, this way you can compute. Same way I have made it here for you, that power loss after second iteration. Of course, this is not exact because we have to move for few iterations, another 1 or 2. So, here also we are writing PS minus JQS is equal to V1 conjugate I1. So, I told you V1 is 1 angle 0. So, V1 conjugate 1 angle 0, and this I1 is actually after second iteration we have seen it is 0.01922 angle minus 35.8 degree. That means, PS minus JQS is equal to 0.0155748. I have taken up to 6-7 decimal places for more accuracy. But for assignment or for exam purpose, if something like is there, I will suggest you consider only up to 4 or 5 decimal places, do not go beyond that, right. Minus J 0.01126, right. That means, PS will be real of this one is 0.1557 per unit is equal to, this is the value, into multiplied by MVA base into 1000 kilowatt, just I showed you, but MVA base is 100. So, it is PS is equal to 0.0155748 into 100 into 1000 kilowatt, that is total input power to the substation real power 1557.48 kilowatt, right. Therefore, similarly, QS will be, this is your QS is equal to minus your imaginary of this one. So, generally QS will be, just compare the real and imaginary. So, QS is 0.011 your 266 into base MVA 100 into 1000 kilowatt, right. Therefore, QS will be 1126.6 kilowatt. That means, this is power input and load is, that means total power loss P loss is, I am writing sum of power loss. Previous thing I wrote P loss and SP loss same, sum of power loss is equal to total your power loss, that is 1557.48, just now we got this one, minus the total load, that is PL2 plus PL3 plus PL4. So, it is in kilowatt. So, 57.48 kilowatt. Similarly, Q loss will be 1126.6 kilowatt minus QL2 plus QL3 plus QL4, whatever load was there. So, loss is coming 26.6 kilowatt after your second iteration, right. This way loss can be computed. So, here during the iterative process I did not check any convergence thing or anything, because then I have to move one more iteration. I request you to do the next iteration of yourself, right. So, that is why iteration means that whatever is the loss was the difference of the loss in successive iteration, and take their absolute value, and if it is less than say 10 to the power -3 or -4 in terms of kilowatt say, then you assume the solution has converged. But when we will take I square R loss, I will show you also I square R loss for there are 3 branches. When I take I square R loss, you find there is a difference is there, because it is not a converged solution, right, still 1 or 2 iteration required. So, after another thing is that your I square R. So, there are 3 branches, So, it is mod I 1 square R 1 plus magnitude I 2 square R 2 plus magnitude I 2 square R 3, everything is a per unit multiplied by MVA base multiplied by 1000 kilowatt, right. So, magnitude is 0.01922 square, and your R 1 is actual value was 0.78 ohm. So, I have divided by their base impedance 1.21, right. Similarly, here also this is the I 2 square, this is the magnitude of I 2, all you have calculated after second iteration, into this is the exact value of R 2, that is 1.62 ohm by base impedance 1.21. Similarly, here also this is the magnitude of current square into 2.19 up 1.21, when MVA base is 100. So, multiplied by 10 to the power 5. Therefore, total power loss here it is coming 60.94 kilowatt, but here it was 57.48 kilowatt. What this difference is, because the solution has not yet converged. When you take say another iteration or another 1 or 2 iterations, so solution will converge, you will find calculating this way this loss or calculating this way this loss, both will be same, identical, right. Similarly, that total Q loss that is magnitude I 1 square x 1 plus I 2 square x 2 plus I 3 square x 3 into 10 to the power 5 kilowatt, right. So, all the I 1s this value is converted to per unit, all x values, and you substitute all these values are substituted, magnitude of I 1, magnitude of I 2 and magnitude of I 3 and the square, right, and these are all x 1 value, it is ohmic values divided by their base impedance 1.21, 1.21, 1 into 10 to the power 5. So, total Q loss is 28.94 kilowatt, but here if you look it is 26.6 kilowatt, slight difference is there, because the solution has not yet converged. That is why this is the your what you call this, that is this difference using this method, but I will suggest you do the third iteration, you will find these two will be very close to this one, and finally solution will converge, right. So, this is actually using your method 1. So, this is the calculation for method 1, load flow. Now, example 2, that is method 2, this is actually same data we will take for the purpose of comparison, same data we will take. So, data same as example 1 of method 1, but here everything rewriting, because R 1 is converted to per unit, R 2, R 3 all are converted to per unit, right. Then x 1, x 2, x 3 all are converted to per unit, everything is in per unit, and meaning is same, R suffix 1, R bracket 1, x 1 is equal to x bracket 1, they are all same. That is why, but still I am making it here, that when you are writing mathematics we are using this one, if you write code you will use this one, right. But question is that I am just making it like this. Similarly, PL2, QL2 all up to PL3, QL3, PL4, QL4 all are same, this PL2 all are same. So, there should not be any question of confusion, right. So, PL2 is 400 kilowatt divided by 1000 0.4 megawatt divided by base MVA. So, 0.004 per unit. Initially also for example 1 all these are given. Similarly, QL2 is 300 kilowatt is equal to 0.003 per unit. Similarly, PL3 is 500 kilowatt, that is 0.5 megawatt, that is 0.005 per unit, and QL3 is equal to 400 kilowatt, that is 0.4 megawatt, so 0.004 per unit, right. And similarly, PL4 is equal to 600 kilowatt is equal to 0.005 per unit, and QL4 is 400 kilowatt is equal to 0.004 per unit, right. Now, that the same example 4.1, this is a branch number 1, 2, 3, sending and receiving end, sending and receiving end, sending and receiving end, right. Here also meaning is same, P suffix 2 and P bracket 2 all are same. Similarly, Q2, R1, everything meaning is same, right. They are identical, same thing. So, for second method initially we have to assume that loss is 0, that means assume initial loss is 0 means that all the branch power losses are 0, that means real power losses and reactive power losses in all the branch you assume initially it is 0, right. Therefore, for J j is equal to 1, when J j is equal to 1, sending end node is M1 is 1, M2 is equal to 2, right. Therefore, M1 is equal to 1, M2 is equal to 2, all these things are written here, right. Similar, then from equation 68, if we go to equation 68, then you will see equation 68 is this one. We wrote AJJ is equal to PM to RJJ plus QM to XJJ minus 0.5 into magnitude VM1 square. When JJ is equal to 1, just now we have given M1 is equal to 1, M2 is equal to 2. That means A1 is equal to P2, here you substitute, JJ is equal to 1 and M2 is equal to 2, here and M1 is equal to 1, here you substitute. So, A1 is equal to P2 R1 plus Q2 X1 minus 0.5 magnitude V1 square. This is say equation 1, this is numerical equation 1. So, initially loss of all the branches are neglected, therefore, total load fed through this node will be PL2 plus PL3 plus PL4. Just repeating this, look, we have taken a very small example, right. This is the electrical equivalent of branch 1 and 2. So, this is branch 1, node 1, 2, 3, 4 electrical equivalent, this is your branch 1, right. So, here everywhere load is there, PL2 QL2, PL3 QL3, PL4, all these things have been explained before, and this is the branch 1 and this is the branch 2. Then what is the electrical equivalent? It will be P2 plus J Q2, right. So, beyond this node, these two branches are there, but we have assumed losses are 0. Then what is the total load fed through this node? It will be P2 will be, here you have load, here you have load, here you PL2 plus PL3 plus PL4, because everywhere that PL2 plus JQL2, PL3 plus JQL3 plus PL4 plus JQL4 load is there. So, P2 will be PL2, then plus PL3 plus PL4. Similarly, Q2 will be QL2, QL3 plus QL4, QL2 plus QL3 plus QL4, right, but loss is neglected. So, that means my P2 will be PL2 plus PL3 plus all in per unit, you make 0.004 plus 0.005 plus 0.006, that will be 0.015 per unit, right. Similarly, Q2 will be equal to QL2 plus QL3 plus QL4 is equal to 0.003 plus 0.004 plus 0.004, that is 0.011 per unit. Voltage at the substation it is known, because it is 1 angle 0. So, magnitude V1 is equal to 1, this is known, right, and R1 is equal to this R1, I told you this is per unit 0.644 per unit, and X1 is equal to X suffix 1, that is 0.3719 per unit. So, all this data you put here in this equation and calculate what is the value of A1. If you do so, A1 will be 0.015 into 0.6446 plus 0.011 into 0.3719 minus 0.5 into V1 square, that is 1 square. It will become A1 will become minus 0.4862401, right. And similarly, from equation 69, another term was there djj. So, djj is equal to a square jj minus r square jj plus x square jj into p square m2 plus q square m2 bracket close, right, to the power half. Therefore, jj is equal to 1, therefore, d1 is equal to a square 1 minus r square 1 plus x square 1, and m2 is equal to 2 for jj is equal to 1, therefore, p square 2 plus q square 2 to the power half. Therefore, you calculate this term r1 square plus x1 square. So, r1 square plus x1 square is equal to this one, right, 0.6446 square plus 0.3719 square is equal to 0.553818. I suggest, I have taken up to 6 decimal place or so, but for the assignment purpose everything I will tell you that you should take only up to 3 or 4 decimal place. I mean, if you for 5538 you can make it approximation 0.554, right. So, I have taken exact one. Then D1 is equal to, we have calculated just now A1 minus 0.4862401. So, it is minus 0.4862401 whole square, right, because it is square, right, minus then r square plus r1 square plus x square we have made it 0.553818. So, substitute here and then it is p2 square 0.015 square plus 0.011 square and to the power half. If you simplify this, D1 will become 0.486042. So, A1 is minus of this thing, very close, only their sign difference is there, but this term and this term they are very close, right. Up to first 3 decimal places these two are almost same, right, but there is a negative sign here. Every iteration you will find magnitude wise these two term will be very close, right, but here it is a negative sign. Next is calculation of voltage magnitude. So, from equation 66 we know that voltage magnitude Vm2 is equal to djj minus ajj half, right, but for jj is equal to 1, m2 is equal to 2, this is the very first iteration going on. So, V2 magnitude V2 is equal to d1 minus a1 to the power half. This all these things continuing for jj is equal to 1, branch number 1, m1 is equal to 1, m2 is equal to 2, right. So, you substitute there d1 is 0.486042 minus, it is minus, and a1 is minus, in bracket it is minus 0.486240, so minus minus plus actually to the power half. If you simplify, magnitude of V2 will come 0.98604 per unit. So, magnitude of V2 is obtained. Now, once V2 is obtained, so loss of branch 1, that is P loss 1 R1 into P square 2 plus Q square 2 upon V2 square. This also I have showed you, right, how to calculate the losses. So, this is the your in this diagram, this is the current I1 and this is the voltage magnitude V2. Therefore, this already I have explained, but once again I am showing P2 minus jQ2 is equal to V2 conjugate I1, right. Therefore, I1 is equal to P2 minus jQ2 upon V2 conjugate. Therefore, magnitude of I1 is equal to root over P2 square plus Q2 square upon V2, right, and therefore, this is magnitude of I1. Therefore, magnitude of I1 square is equal to P2 square plus Q2 square, right, divided by V2 square, right. Or for branch 1 power loss, if you want R1, then I1 square is equal to R1, in bracket I am putting P2 square plus Q2 square upon V2 square, right. So, this is real power loss. Similarly, if you multiply x1 with this term, then that will give you reactive power loss. So, here P2 every year I am telling this P2 means this bracket P2, Q2 means this bracket Q2, like this, right. Therefore, when you compute the your what you call the loss of branch 1, it is P loss 1, that is loss of branch 1 is equal to R1 into P2 square plus Q2 square upon V2 magnitude square. So, R1 is 0.6446 into P2 is 0.015, first iteration is going on, plus 0.011 square divided by 0.98604 square. So, P loss 1 will be 0.000223939 per unit, right. Similarly, Q loss 1 will be x1 into P2 square plus Q2 square upon V2 square. So, it will be 0.3719, 0.015 square plus 0.011 square by 0.9860. Actually, this term remains same, only here it is multiplied by R, here it is multiplied by X, right. Therefore, Q loss 1 is 0.00132334 per unit. This is per unit only, later we will convert to the real unit because we have to go for the iteration, right. Similarly, first iteration is continuing. So, similarly, for jj is equal to 2, for jj is equal to 2, m1 is equal to 2, all this I have explained, and m2 is equal to 3. Therefore, P3 will be now actually it will be PL3 plus PL4, same the total initially loss are all neglected. So, P3 is equal to PL3 plus PL4, and whatever loss we have calculated, that is loss of branch 1 not branch 2, loss of branch 2 not your branch 1, whatever loss you have calculated, this is for loss of branch 1 not branch 2 or 3, right. Therefore, PL3 plus PL4 is this much 0.011 per unit, and your Q3 is equal to QL3 plus Q4, that is your 0.008 per unit, right. So, now from the same equation for jj is equal to jj is equal to 2, you calculate A2 now from this equation only, whatever from equation 68 only put jj is equal to 2 here only, right, here only. So, in that case you will get A2 is equal to P3 R2 plus Q3 X2 minus 0.5 V2 magnitude square. So, substitute all the values you substitute. So, A2 will be 0.011 into 1.3388 plus 0.008 0.5454 minus 0.5 and this is the voltage magnitude V2 square. So, 0.98604 square. So, A2 is becoming minus 0.4670474, right. This is A2. All R2, X2, V2 are R2 square plus X2 square, everything is written here. I have recalculated and I am writing here for such that when you will go through this slide, at that time readily available in front of you, that is why I have written. Similarly, from this equation, that again your DJJ equation I come, that is equation 69. This is your equation 69, this DJJ, here put JJ is equal to 2, right. Accordingly, it will be your what you call that M2 is equal to 3, it will be Q3 P square 3 plus Q square 3 and it is R square 2 plus X square 2. So, D2 will be A square 2 minus your R square 2 plus your X square 2 in the P square 3 plus Q square 3 to the power half, right. Therefore, put all these values, it is D2 is equal to minus 0.4670474. When you will do the assignment and repeating, I am that assignment or example, if something is there, you will take only up to 3 or 4 decimal, not more than that, right. Minus this is R2 square plus X2 square, R2 square plus X2 square in per unit I have computed here, right. So, substitute and it is your P3 square plus Q3 square, right. P3 is given, Q3 is initially given, right. So, if you make D2 will be 0.466633, this is D2, right. Then V3, then magnitude of V3, it will be your D2 minus A2 half to the power half, right. Again from this voltage equation it is coming, whatever we have computed this voltage equation, this is coming, that is I think it is 66, this is equation 66, from this here it is coming from this equation, right. Therefore, your V3 will be your D2 minus A2 to the power half, substitute 0.4666333 minus in bracket minus 0.4670 whatever it is 474 to the power half. So, magnitude of V3 will be 0.966271 per unit, right. Then will be loss of branch 2. Thank you, will be.